Hello everyone and welcome to Cambridge CIE IGCSE 0606 additional mathematics course. In this video we will be covering chapter 6 logarithmic and exponential functions. So let's get started. Now before we go into the chapter, let's understand what a logarithm is. So if you look here, if you have an equation of this type 2 to the power x is equal to 8, how you would have been solving it till now is you would say that well, 8 is equal to 2 cubed, and then if you actually look at them and compare them, you can see that 2 is equal to 2, so x must be equal to 3, and that is how you would solve it. Well, logs are actually sort of inverses of that exponential thing, so like these two are inverse of each other, so 2 to the power x and log base 2 of x are actually inverses of each other. So what you can do is you can take log base 2 on both sides. So you get log base 2 of 2 to the x is log base 2 of 8, and this is a function in your calculator. So when you do this, actually this gives you x. We'll cover this later down. And then if you pick up your calculator and you type in log base 2, so 2 in the spot that is at the bottom and 8 inside the brackets, you get x is equal to 3, which is this. So that's basically what logarithms are. Now, notation basically, if you have anything to the base 10, can just be written as log x, which can be simplified to lgx. So if you see this, don't like worry, there's no base. It's actually just implied that it's 10. And anything written to the base e, which will cover what e is written as ln x. So again, don't worry about that. Now, um, let's actually talk about e for a second. So e is a special irrational number. So like e cannot be written as p over q. It cannot be represented as fraction. Similar to how pi is 3.14 so on so on so on. E is also 2.71 so on. For forever. There's no repeating pattern or anything. 2.72 actually, I think. Yeah, E will be 2.72 and repeating so on. Now, the special thing about this E is that if we look at its graph looks like this, and this will be 1. If you were to draw a tangent, so let's say we draw, let's say here, imagine this intersects. If we draw a tangent at this point, let's say this is x is equal to 2, and this is e squared. The gradient of this tangent m will also be e squared. Basically, the gradient of a tangent at any point is equal to this y coordinate. This is actually the more formal notation. This is the derivative of e to the x is e to the x. This is part of the calculus chapter, chapter 14, which we will come to later, so you don't need to know it yet. But that is basically what e is. So log base e of x is ln x, or called the natural log of x. So again, e functions the same as any other number. E to the power x is equal to e squared means x is equal to 2. Again, this is the thing in terms of logs. So one more thing, as we discussed earlier, 2 to the x and log base 2 to the x are inverse. Same way, e to the x and log base e or ln x are also inverse of each other. Now, the graphs of e to the x are very important for our syllabus. So this is what e to the x looks like, as we talked about before, and its inverse ln x. So if you look at them, they're actually reflections in the line y is equal to x. Here, same thing, y is equal to x. They're actually reflections of each other in this line. So what happens, let's talk about some transformations of e. So if you multiply it by a scalar, well, the curve is actually going to be a bit steeper, and then the y coordinate will just become k. If you multiply the exponent by an the curve actually becomes steeper. So as you keep increasing n, the gradient after this point will actually keep increasing. Now, if you add a constant a to the, this is a, you will actually see that it's translated up because e to the power 0 is 1, so the y-intercept is actually a plus 1. Now, yeah, one important thing about these graphs is something called asymptotes. So basically, if you look at this graph, as x tends to negative infinity, this graph will continue like this forever, and it's going to get closer and closer to the y-axis. So it's going to like get closer and closer, sorry, to the x-axis, but it will never touch it. That is called, so the x-axis is basically the asymptote. The graph will keep approaching it, but it will never actually touch it. Same thing for ln x with the y-axis. So if you look here, the line y is equal to a is actually the asymptote. So here, because it's e to the power x plus 0, y is equal to 0 is the asymptote. Y is equal to a will be the asymptote here. Alright, now moving on to ln x. Again, if you multiply the curve by some k, that will be similar to this one. We'll get to that actually somewhat of a derivation soon enough. So as k increases, the gradient also increases after the intercept. Now ln ax looks like this, same thing, but it's just the intercept with the x-axis is now 1 over a. And ln x plus b, where x is where the plus b is inside the brackets, is the asymptote, then becomes negative b, and the x-intercept becomes negative b plus 1. If it was outside, y is equal to ln x plus b, your graph is actually bound to look something like actually that won't have an effect that I can think of. Let me reconfirm that. Let's see. If we look at Desmos over here, you have y is equal to ln x, and then you have y is equal to ln x plus 3. Okay, yeah, there is somewhat of an effect. Obviously, everything is then translated upwards by 3, so probably something like this. Where, and this will be ln x, so yeah, y is equal to ln x plus b. Yeah, probably should know that also as well. Okay, now let's end the chapter with some properties of logarithms. What is basically the algebra part of this. So if this isn't clear, this is actually log. Let me just 1 second. M multiplied by m. Yeah, m multiplied log of m multiplied by n is same as log of m plus log of n. Any base, it doesn't matter. I'm just taking 10 here, so I don't have to write the base. Same thing here. If it's m divided by n, then you just do subtraction because it's actually just m multiplied by 1 by n. So it becomes negative. So the log of 1 by n is actually just negative log n. Right, we'll come to that soon. That's based off this property because log of 1 by n is equal to the log of n to the negative 1. So the negative 1 comes out, similar to how this a is put in front of the log here and it's multiplied. So that becomes log of m raised to a is 8 times log of m. Then log base anything of 1 is 0 because anything raised to 0 is equal to 1. Then same thing, log of, so uh, log base 10 of 10 is equal to 1. That's because 10, anything raised to 1 is again itself. So that's that property. And then this basically, because they're inverses of each other, applying them on either of them cancel the thing. Again, same thing here. 10 log base 10 of x will give you x. Same thing here, log base 10 of 10 is 1. And now this is actually the most important formula of this chapter, is called change of base, where basically if you have log base a of x, we can change the base to be something, some other number like b, any number. And so you can say that this is equal to log base b of x all over divided by log base b of a. Now note, you can't actually cancel log to make this x by these, that doesn't work. The thing you can just straight up do is just switch these two around. So a goes in place of x, x comes in place of a to give you 1 over log base a of x. Obviously log base a of x cannot equal log base x of a unless as long as a does not equal to x. So that's the thing, and that's about it for this chapter actually. Thank you for watching.